This program is brought to you by Stanford University. Please visit us at stanford.edu.
Good evening and welcome to the Stanford Summer Science Lecture Series. My name is Steve Graham and I serve as Associate Dean of the School of Earth Sciences. It's my very great pleasure this evening to introduce tonight's speakers, Drs. Mary Lou and Mark Zoback, both longtime friends of mine and former grad school classmates here at Stanford. If you watch local TV news, you've almost certainly seen one or both of these two in the past, because every time there's an earthquake of any significance in the world, they are instant celebrities. So tonight you'll have the opportunity to interview them for yourselves. Mary Lou is currently a senior research scientist with the USGS Western Earthquake Hazards Team here in Menlo Park. She was especially visible here in the Bay Area this year as chair of the steering committee for the 1906 Earthquake Centennial Alliance, a nonprofit coordinating more than 280 groups and organizations that put on events commemorating the centennial of the earthquake. She has 3 degrees from Stanford, was chief scientist of the USGS Western Earthquake Hazards Team, is past president of the Geological Society of America, and is a member of the National Academy of Sciences. Her husband, Mark Zoback, is no less accomplished. He's the Benjamin Page Professor in the Department of Geophysics. He obtained his bachelor's degree in Arizona before he discovered Stanford, where he got 2 more degrees and a wife. He was affiliated with the USGS for a dozen years, including a stint as the chief of the branch of tectonophysics, before joining the Stanford faculty in 1984. He's been very visible on the university scene, among other things having served as the chair of the faculty senate. Most recently, you've seen him interviewed on TV as a frequent spokesman for and co-principal investigator of the San Andreas Fault Observatory at depth, which is the exciting project which entailed drilling a couple of miles into the San Andreas Fault a year or 2 ago, near Parkfield, in order to instrument the fault and take up long-term monitoring. Tonight, Mark will lead off with a global perspective on seismic activity, and Mary Lou will follow with comments more specifically directed towards seismic issues here locally in the Bay Area. After that, you'll have the opportunity to ask them directly about all things related to faults and earthquakes. No doubt, including everyone's favorite question, when's the big one coming? Before we begin, and I turn the mic over to Mark, a couple of practical matters I want to mention. First of all, you should be aware that this particular session is being videotaped, and that taping will be posted on Stanford's iTunes. A second thing, we, as it turns out, unfortunately, are under the flight path of the hospital's medevac helicopter. So if, in fact, that helicopter flies over at any time during the lectures, the speakers will simply pause for a moment and let the noise pass. Then finally, the next lecture in this series promises to be a very interesting one, sort of a Da Vinci Code-like historical mystery. Uwe Bergman is going to talk about imaging of a lost Archimedes document that was hidden underneath some forgeries. Sounds like a great mystery, doesn't it? So please join us for the next lecture series, which is in early August. With that, I'll turn it to Mark, who will talk about global seismicity issues. We have a veteran of a prior lecture, and clearly there are others. No, the lawn sprinklers I don't think will go off tonight. Mark Zoback.
I guess we'll all find out about the lawn sprinklers together. Well, it's a pleasure to be here this evening and talk to you about earthquake hazards. And I want to do 3 things in my comments tonight. First, I want to talk about earthquakes at a global scale and talk about actually the devastating consequences of earthquakes in the developing world. I want to go on to talk about intraplate earthquakes, earthquakes that occur within the giant tectonic plates that move across the Earth's surface, and the special hazard that they pose, and what we know and don't know about their occurrence. And then finally, I'll address everyone's second favorite question, and that is, can we predict earthquakes, or when will we predict earthquakes, and why are you predicting earthquakes and not telling us about it? So, now when I conclude, Mary Lou will focus about earthquake hazards in the San Francisco Bay Area, and we've agreed to keep our comments relatively short to give all of you plenty of time for questions. Now, in the news this week, reports of an earthquake and a moderate tsunami in Java on July 17th resulted in on the order of 500 fatalities. And unfortunately, when it comes to earthquakes in the developing world, this is sort of business as usual. Now, we printed off copies of an essay that I wrote for the Washington Post that attempted to address the question of why must earthquakes be so devastating. The article was published in January 2004 following a now mostly forgotten earthquake in Bam, Iran that killed 30,000 people. Now, in that article, I cite some of the other relatively recent devastating earthquakes in the developing world. In 1976 in Tangshan, China, between 250,000 and 500,000 people were killed in a single earthquake. In 1999 in Izmit, Turkey, there were 17,000 dead, 600,000 homeless. 2001, Bhuj, India, 20,000 dead. Now, these are very frightening numbers, but they pale in comparison to what we know about some of the largest events during human history. In 1556 in Shenxi, China, which is just on the east coast of China, north of Korea, there was an earthquake that produced an estimated 800,000 fatalities. In 1138 in Aleppo, Syria, 230,000 fatalities. In 1922 in Gansu, China, which is more like central northern China, another earthquake with 200,000 deaths. Now, to paraphrase the first sentence of that Washington Post piece, the toll from the Iranian earthquake, at least 30,000 dead, is difficult to comprehend. Unfortunately, we can predict with a reasonable degree of certainty that sometime in the next few years, in a country with buildings unprepared to withstand strong shaking, a catastrophic earthquake will happen again. Now, making such a statement took no particular prescience because such devastation is, unfortunately, business as usual in the developing world. But less than a year after the article came out, the magnitude 9 Sumatran earthquake and tsunami of December 26, 2004 killed an estimated 300,000 people. Less than 10 months after that, the magnitude 7.6 earthquake that hit the Kashmir region on the India-Pakistan border killed an estimated 80,000 people. Now, it's indeed a sobering fact that if we look over this long period of historic time and these devastating earthquakes that have occurred, that were they to recur today, the losses in many cases would be nearly as severe as they were hundreds of years ago. And that's because in many parts of the developing world, sun-baked mud brick construction and heavy clay tile roofs still serve as shelter for literally hundreds of millions of people. In earthquake country, such unreinforced masonry structures are death traps, just waiting to happen. In larger cities, buildings are sometimes built with floors continuously added until the lowest levels begin to show some sign of yielding from the weight of the stacked up floors, and at that point they stop building. Well, you can imagine that even a moderate amount of shaking is enough to cause collapse. And in fact, one image that's particularly imprinted on my mind is that of relief workers standing on what had been a 6-story building in Mexico City that had pancaked, just totally collapsed in response to shaking from an earthquake that was over 200 miles away. Now, most of you are familiar with plate tectonics, the idea that these thick lithospheric plates, about 60 miles thick, move across the Earth's surface. There are about 12 or 13 plates, and their motion with respect to each other produces earthquakes at their boundaries. The Mexico City earthquake resulted from the subduction, the fact that the Cocos Plate was subducting under Central America. The Sumatran earthquake resulted from the fact that the Indo-Australian Plate is subducting beneath southeastern Eurasia. The earthquakes in the San Francisco Bay Area result from the fact that the Pacific Plate moves to the northwest with respect to the North American Plate. But three of the most devastating earthquakes I mentioned, those in China, all occurred, as well as the one in Bhuj, India, all occur in intraplate regions, far from these plate boundaries. Now, intraplate earthquakes are particularly difficult to understand. They're not the result of the two plates moving past each other. And earthquakes on any individual fault will occur very infrequently. In fact, some of the killer faults responsible for history's most damaging earthquakes had not moved for thousands of years prior to the devastating event. Now, we're not immune to intraplate earthquakes in the United States. In 1811, 1812, three very large earthquakes, estimated at magnitude about 7.5, occurred in the New Madrid area. That's southeastern Missouri, northeastern Arkansas, western Tennessee, western Kentucky. A very large earthquake struck the Charleston, South Carolina area in 1886. And should those events recur today, the consequences would be extremely serious because building codes in intraplate areas, far from the plate boundaries, do not generally incorporate the possibility of seismic shaking, even for critical structures such as nuclear power plants and other critical facilities. Now, work that Mary Lou and I did back in the 1980s showed that the forces that result from plate tectonics are actually transmitted through the plates. So we understand where the force comes from that produces these earthquakes. But what we still do not understand today, and many scientists are engaged in studying, is what characteristics of an intraplate area make it prone to such an earthquake with respect to surrounding regions. Because the earthquakes occur so infrequently, you can't just go, run around with a red flag telling everybody to worry about earthquakes all the time. At any given place, the earthquake occurrence is going to be very infrequent. But when it does occur, if you're totally unprepared for it, the earthquake's consequences will be that much more damaging. Well, so what do we do about all this? Well, in the developing world, and to a degree we still need to do it in the developed world, we need to practice earthquake engineering. The 1995 Kobe earthquake in Japan was an excellent example of the importance of earthquake engineering. 5,500 people were killed. 100,000 buildings were essentially unoccupiable after the earthquake. But in almost every case, the deaths that occurred in the earthquake could be traced to structures that were built before the utilization of modern building codes that incorporated earthquake safety. Now, many of the buildings that had been built recently in accordance with the codes were severely damaged. But people were not killed in those buildings. The buildings were damaged, but the lives were saved. Now, earthquake engineering and building codes and enforcement sort of go hand in hand. And even the best earthquake engineering will not work unless the codes and principles are applied with vigilance. Having essentially the same codes, for example, in a developing country as we do in California, doesn't protect anyone if those codes aren't enforced. And the recent earthquakes in Turkey were a very excellent example of that, where basically bribery and corruption prevented construction from occurring in accordance with perfectly adequate codes, but if they're not enforced, they're not going to do their job. The third thing we need to do, of course, is disaster preparedness. And this is a matter of individual action, local government, state government, federal government, international agencies. And since Mary Lou will talk a lot more about this, I'll not say too much, but I would like to put a brief plug in for Geohazards International. Geohazards International is located over here in the Town and Country Shopping Center, and it is run by Brian Tucker, the former state seismologist for California. And Geohazards International devotes all of its efforts to reducing earthquake hazards in the developing world, and it's a remarkable organization and truly worthy of everyone's support. Now, the fourth thing we need to do is continue fundamental research on earthquake physics and understanding how earthquakes work. And we need to determine whether or not earthquakes are predictable. It's an obvious question. Now, the good news is that there are many things about earthquakes that we can predict already. And as Mary Lou will illustrate for the San Francisco Bay Area, scientists know where big earthquakes are likely to occur in the future, which faults are likely to produce the earthquakes, roughly how big they're likely to be. We know what their long-term probability is likely, the probability of recurrence of another earthquake on one of these faults. So we know where they are, we know roughly how big they'll be, we know roughly how likely they are to occur over some period of time. And you can model those earthquakes in a computer, and you can actually predict the effect of those earthquakes. So it is possible to plan for them and get ready. And it's really fortunate that we all live in an area that's so intellectually endowed with the USGS, two great research universities, and many other outstanding institutions in the San Francisco Bay Area. The collective result of this, makes this collective result of the scientists at these organizations make this kind of information available. But what's been done here can be done elsewhere. And it's simply a matter of committing the resources and having the will to see that it gets done. Now, the same is not true for short-term earthquake prediction, which many consider the holy grail of seismology. Now, earthquake prediction, short-term earthquake prediction, periods of days to weeks, would not prevent most of the physical damage that accompanies large earthquakes. But it would be enormously effective in reducing the death toll, especially in the developing world. Now, in 1975, a large and very severe earthquake in Haicheng, China was successfully predicted, and thousands, if not tens of thousands, of lives were saved. But since then, there has been no scientifically acknowledged accurate earthquake prediction, and there is widespread doubt among many seismologists that, in fact, short-term earthquake prediction is even possible. An experiment had been going on for a couple of decades in Central California in the Parkfield region, where a moderate magnitude 6 earthquake had been expected. It occurred in September of 2004, and even despite the fact that it was a fairly heavily instrumented area, there were no anomalous signs prior to the occurrence of the earthquake. In fact, many suspect that the Haicheng prediction may have been fortuitous, as the area had experienced numerous foreshocks. These are small earthquakes which, in some cases, lead up to the occurrence of a larger event. So after almost 30 years with no successful predictions and no apparent progress toward prediction, many seismologists have all but given up on the problem. But still, I think there are reasons for optimism. And it's an exciting time that we live in. For example, GPS technology, which all of you are familiar with, maybe you drove here using it in your car, can be used with tremendous precision when the GPS receivers are mounted permanently and the relative distance between 2 points on the Earth's surface is measured repeatedly through time. These instruments have revealed slow slip events associated with the deep part of subduction zones in Japan, in Cascadia, in Central America, and now recently on the San Andreas Fault in Central California. In other words, below the sections of the fault that are cold and brittle and break suddenly and release tremendous energy in an earthquake, down at the depths where we always thought that the Earth was so hot that the faults just slid stably in almost a continuous and maybe somewhat boring way, we find suddenly by making new observations that that is not true. That in fact, the faults are slipping episodically at great depth. And what we are all very keen to learn is whether one of these aseismic episodic slip events will in fact be the straw that breaks the camel's back, will be the event that eventually triggers the earthquake that has, resulting from the accumulation of strain energy over long periods of time. Now, as a result of a new program of the National Science Foundation that's being carried out in collaboration with the USGS, a program called Earthscope, 800 more of these permanent GPS instruments are being put throughout all of Western North America, along all of the active faults. They're very useful in volcanic areas as well. And time will tell, what the role of these episodic aseismic events are and their, whether or not they are in fact precursors to more devastating consequences. But for the first time we see for the first time we looked, and for the first time we've seen things happening deep within the Earth that may hold promise for short-term earthquake prediction. Another component of Earthscope is the experiment Steve mentioned, the San Andreas Fault Observatory at depth, which I helped lead. We have now successfully drilled through the San Andreas Fault and are in the process of building an observatory within the fault at the depth at which small earthquakes repeatedly occur. And so for the very first time in the near future, we will be able to monitor the inside of a fault before, during, and after earthquake nucleation. And we will know whether, in fact, there are signs that the earthquake is coming. Does the fluid pressure in the fault change? Does the fault begin to move slowly before it accelerates? Does the surrounding region move slowly, therefore loading the patch that eventually slips in the fault? Well, I can assure you that the geophysical literature is full of hypotheses about what might happen deep inside a fault zone, but we'll have the chance for the very first time to find out. To conclude, it's clear that as a society, we need to implement earthquake engineering and preparedness programs everywhere, especially in the developing world. And we need to continue to do everything we can to better understand how earthquakes work. Perhaps someday we will develop prediction capabilities that we can trust and rely on. And that will, in fact, have widespread benefit to hundreds of millions of people who live in quake-threatened areas around the world. But if we don't, if we find that earthquakes are unpredictable, this same research will lead to a much better understanding of long-term earthquake hazards and dramatic improvements in our knowledge of how the Earth works. And my view is that this is not a very bad fallback position. Thank you very much.
Thank you all for coming tonight. I'm going to be talking about events a little bit closer to home, specifically the earthquake threat here in the Bay Area. But I thought I'd begin first by taking a step back and a step back in time. Mark talked to you about what's going on today in the present time in earthquake science. And I'd like to take us back to the birth of modern earthquake science here in the United States. And that was actually here in the San Francisco Bay Area. And we really date the birth of earthquake science to the study of the 1906 earthquake. First of all, I'd like to conduct a poll. How many of you experienced the 1989 Loma Prieta earthquake? How many in the audience? A good percentage, but an awful lot of you were either too young or lived somewhere else. That was a relatively small earthquake compared to the 1906 earthquake. The 1989 event occurred in the Santa Cruz Mountains. It was about a magnitude 6.9. It broke a fault, probably not the San Andreas Fault, but a nearby fault. It broke the fault for about 25 miles. The 1906 earthquake was a magnitude 7.9. It doesn't sound so different, 6.9, 7.9, but it's more than a factor of 30 in terms of the energy that was released by the earthquake. So it broke the San Andreas Fault for 300 miles, virtually all of Northern California, from San Juan Bautista up to Cape Mendocino. It would take 30 Loma Prieta earthquakes, all occurring at the same time, to equal the energy released by the 1906 earthquake. So we have a range of earthquakes in the Bay Area, and the 1906 is probably the largest earthquake that we could expect to strike Northern California. When the earthquake occurred, I must admit the scientists were pretty excited. They went out right away, as we do, we're curious, and started studying the event. And actually 3 days after the earthquake, the Governor Pardee, commissioned a scientific study of the earthquake itself and appointed a commission of 8 scientists led by Andrew Lawson, a professor at UC Berkeley, and they were to study the effects of the earthquake and write a report on it. It was an unfunded mandate. He did not provide any money, but I don't think anything would have kept them home. And they actually raised some funds from the Carnegie Institution in Washington, D.C., and went out mapping the fault. And what they found is that the fault ruptured onshore about 200 miles. They followed it, they mapped it. In many cases, we were a young state, there weren't very good maps, but they made their own maps because they realized it was important to know where the fault broke. One poor soul actually drew the short straw and was told, follow the fault for as long as you can. He got on his horse with very crude maps and followed the fault all the way into Southern California. We now know it extends more than 700 miles along much of the length of California. It was mapped at that time. It was known there was a large earthquake in Southern California in 1857. 1,000 people lived in the LA area at the time, and he could show, in fact, that that earthquake had occurred on the same fault. Studying the fault in Northern California, they also recognized that this was not a random event. A similar kind of earthquake had happened in the past, and they could tell this by looking at very subtle topographic features along the fault. Depressions, which they called sags or sag ponds, a term we still use today. Those of you familiar with the fault in this area know as it goes through Portola Valley, there are some of these depressions. One's right behind the sequoias. The fault runs right behind the sequoias. And these subtle features, actually, these little ponds dropped down a little bit in the 1906 earthquake, and nearby ridges went up a little bit. So they were able to conclude that this earthquake was part of an ongoing process. And even though most of the slip in the earthquake was horizontal, blocks slid past one another, they recognized there were small vertical adjustments, and these had happened repeatedly. And because the features were so subtle, they figured it had to happen on the order of several hundred years. Otherwise, erosion would have wiped them out. So they established it was a recurring event and maybe on the order of a few hundred years, which we now know is the case. They established that it was a major through-going feature that had had a fault in Southern California. And they learned something else, too, really important. Again, we were a very young state. They were busy surveying the state, just literally mapping the state out. And one of the things they were doing with the surveying was something we call triangulation. You stand on one mountain peak and you measure the angle to 2 distant mountain peaks. And they noticed those angles were disrupted by the earthquake. So they quickly went back out and resurveyed all of Northern California. And they were actually able to determine how much the fault moved at the surface by looking at the change of angles. And the geologist had already gone around and mapped how roads were offset. Fences were offset by the fault. Highway 92 going out to Half Moon Bay, fortunately, was only a gravel road. It was offset 9 feet by the fault. The fault runs up through Crystal Springs Reservoir on the eastern side, right along the eastern shore, and the road was offset 9 feet. That's going to happen again. If you live in Half Moon Bay, I hope you have tennis shoes or hiking boots in your trunk, because you won't be able to drive home. There will be no road over to the coast open when the fault breaks again. So they established that this was a recurring event. It involved horizontal slip, and that was a little puzzling. They were aware of faults. We knew about faults, but they thought they slipped vertically. Gravity could cause a fault to slip vertically, or if you shove two blocks together, one could ride up over the other with a vertical motion. But it really wasn't clear why these things were moving horizontally, and if you think about it, at the ends, there's a problem. And in some places along the fault, there was as much as 30 feet of slip. So if we were standing here, I would have shifted over 30 feet relative to you guys. So there was a lot of movement. But nonetheless, they followed their observations. They documented that it was horizontal slip. And it really wasn't until plate tectonics that Mark talked about that was really established more than 60 years later that we really understood what was loading this fault. And we know today that all the faults in the Bay Area, which are shown here on this map in front of me, and I urge you all to pick up a copy, if you haven't gotten it yet, of this handbook, Putting Down Roots in Earthquake Country. It explains a lot of what I'll talk about tonight about why earthquakes occur here, but it also is a earthquake preparedness guide. Take multiple copies, give them to your friends and neighbors. We would really appreciate that. So we have a multitude of faults in the Bay Area, 7 major fault zones. They're all parallel to one another, and they're all striking roughly northwest. And that's to accommodate the plate tectonic motion of the Pacific Plate sliding past North America, relatively moving to the northwest. Now, earthquakes occur rarely. On most of these faults, they occur every few hundred years, maybe 150 to 200 years. In between times, though, the plate motion continues, and it continues at depths where the rocks are warm and they can sort of flow like honey. And that's actually loading the upper part of the Earth's crust where these faults exist. And at some point, that loading, and think of it as shearing a thick elastic sheet like this, at some point the faults are going to give. You're putting a lot of energy as you shear that elastic sheet. And that energy is going to be released suddenly in an earthquake, a rapid slip. You can think of it as stretching a rubber band, and then the rubber band snaps. The energy, the sound you hear is seismic energy. That's the energy that you put into the system is being released in an earthquake. All of this was recognized from studying the 1906 earthquake. The piece that was missing is they had no idea why these blocks were sliding horizontally past one another. Today we have continuous GPS stations throughout the Bay Area, as Mark mentioned. We have a station out on the Farallon Islands off San Francisco, and we have a station way up in the Sierra foothills in the Gold Country. Those 2 points are moving relative to one another parallel to the fault system at a rate of about 1.7 inches a year, about the rate that your fingernails grow. So these points are moving all the time. We're not having earthquakes all the time. The faults are locked, but the motion at depth is continuous, and that's what's loading the faults. And that motion actually gets divided up on these 7 faults. So at any given point, each fault is in a different point in its earthquake cycle. So we have a period of slow strain accumulation and then sudden release in an earthquake. And that's what produces the earthquakes in the Bay Area. Now, the San Andreas Fault and the entire San Francisco Bay Area was very active in the 19th century. It was a very different place here than it has been in the 20th century that most of us are familiar with. In the 70 years leading up to the 1906 earthquake, there were 18 magnitude 6 or greater earthquakes throughout the San Francisco Bay region. That's a magnitude 6 or larger earthquake every 4 years. Not what we have experienced since 1906. The 1906 earthquake not only relieved the strain on the San Andreas Fault, but because these faults are so close together in parallel, it actually relieved accumulating stress on all the faults in the Bay Area. So it literally shut down the seismicity. So one could actually conclude that one of the most social-political legacies of the 1906 earthquake was this phenomena that we call a stress shadow, basically this aseismic period that allowed the Bay Area to grow into what it was today. I think if we were having a magnitude 6 or larger earthquake every 4 years, a lot of people would decide it really isn't worth living here with the high house prices and everything else. So we've learned a lot since the 1906 earthquake. We learned a lot, and a lot of what we are still doing today builds on what we learned from the 1906 earthquake. But we have been doing some new things too, and I'd like to talk about them for a few minutes and then get to the specific earthquake threat in the Bay Area. One of the things that we know how to do now is recognize and map active faults, and that's where this map came from. We also significantly have been able to work out, because we have a short historic record in the Bay Area, we've been able to work out the past history of earthquakes on the faults. This is a field we call PaleoSeismology, and we do this by literally digging a trench across an active fault in a place, in a depression, place where soil's been accumulating, and we actually look at and date disrupted soil layers. And fortunately for us, when a fault occurs, when it gets to the very near surface, up into the dirt, it doesn't always break in exactly the same place. So when we dig a trench, say 20 feet wide across the fault, we'll see multiple breaks. And the deeper the soil layer, the more offset it'll be. And from carbon plant material trapped in the soil, we can actually date the soil layers and then get an idea of the timing of past earthquakes. We've done that for nearly all the major faults in the Bay Area now, and we are starting to build a history. One of our best sites is along the Hayward Fault. This is the fault that runs up the East Bay through the UC Berkeley campus, right through the football stadium. I'm always a little worried watching big game. It runs up the East Bay, and near the southern end in the town of Fremont, those of you that have taken the BART station at Walnut Avenue, the southern terminus of the BART line, they've actually filled in one of these depressions along the Hayward Fault there. The fault runs right through the parking lot, and they literally filled up the depression to create the parking lot. Well, across the street, next to the condominiums, right next to the depression, we were able to put in a series of trenches there. And it turned out to be a good site because this had been a pond at the time the Ohlone Indians were here. They used to camp on the sides of the pond, lots of organic material. We could see ash from big fires in the pond. And when we looked at the soil layers there, we could actually date the last 11 earthquakes on the Hayward Fault. And on average, so we go back nearly 2,000 years, there's been a big earthquake about a magnitude 7 every 150 years. The last one we know about, it was in 1868. It was known as the Great San Francisco Earthquake until 1906 because it did a great deal of damage in San Francisco. And so the most recent one was in 1868. In fact, if we look at the 4 most recent earthquakes on the Hayward Fault, they're about 132 years apart. So I think you can all do the math. We're really worried about the Hayward Fault. We're worried about it because it's close to the end of its earthquake cycle, and there's a lot of variability in that. There's no guarantee. But we're also worried about it because it runs right through the heart of the East Bay region. All of our major freeways cross it. All of our gas lines, our water lines, everything we depend on crosses that fault. It runs through hospitals, city halls, police stations, fire stations. When this earthquake occurs, it's going to be devastating. Now, Mark was talking about prediction, and we've already touched on the point that it's not possible to do a short-term prediction of the timing of an earthquake, but we've gotten very good at predicting the likely effects of earthquakes. We know where the faults are. We've mapped the major faults. By looking at streams that have been offset, we can get some idea of how much of the fault slipped in past earthquakes. That tells us about the size. And we have this additional constraint that we know what the plate motion is that loads it. So in the end, you can only get out of the system as much energy as you put in from plate motion. So we have a lot of constraints. So we know the long-term likelihood of earthquakes, but we also are getting very good at predicting what the effects will be. And of course, the most common effect of an earthquake is going to be very strong shaking. And we know a couple of things about that. Some of those we learned from 1906. And then we learned that soft material shakes more strongly than hard rock. So the people that were living along the margins of the bay in soft material suffered the most damage. That's where we saw the most disruption. We also know there's additional effect along the margins of the bay and anywhere you have sandy soil that's saturated with water. And this is a phenomenon we call liquefaction. Really strong shaking literally turns the ground into something like a liquid. Quicksand is a liquefaction phenomena. And when the soil loses its strength like that, it rips roads apart, sidewalks apart, it will rip runways apart. All of our airports in the Bay Area are built on fill. The Bayshore Freeway is mainly built on fill, as is much of 880 in the East Bay. Liquefaction is a phenomena that we are going to face. It's the result of very strong shaking in these special soil conditions. And as you can see, we've got multiple faults in the Bay Area. They're all fairly closely spaced. So they're truly, in terms of earthquake shaking, there's no safe place in the Bay Area. Because we have so many different faults, every part of the Bay Area at some point in the future is going to be shaken very strongly. Another phenomena that we've been able to actually quantify and do modeling for is the fact that basins, valleys underlain by thick stacks of sediment, tend to actually capture seismic energy. You can kind of think of it as shaking a bathtub, and then the water will tend to slosh in the bathtub. Well, that phenomena happens with seismic waves, and modeling we've done shows that the Santa Clara Valley or Silicon Valley is underlain by thick pile of sediments. And for the 1906 earthquake, we've recently recreated that. We've got some wonderful 3D animations on our USGS website, and I'll give you the address for that in a minute. But what we found is that the shaking in the Santa Clara Valley, Silicon Valley, probably was as much as 2 feet back and forth at a rate of about 2 feet per second, and that went on for many tens of seconds. So long after the earthquake went past, and the earthquake, I should say, took 90 seconds to happen. It began offshore from San Francisco, it broke northwest up to Cape Mendocino, and it broke to the southeast down to San Juan Bautista. But at any given point, the earthquake kind of came and passed by, but in basins like Santa Clara, like the Livermore Valley, like the basin underlying Santa Rosa, there was very strong shaking that lasted for many tens of seconds. So even buildings, streets, things that can survive a few, 5, 6 seconds of shaking, if that goes on for 60 seconds, they're not likely to survive. So we've got myriad of faults. We've got a lot of soft soil around the margins of the bay. We've got the conditions for liquefaction and the likelihood now of future earthquakes. I've mentioned paleoseismology, the fact that we can get these histories of past earthquakes. We can look at the historic record to know when was the last time we had an earthquake on each of those faults. And when we put all that together with the constraint that we know what the overall loading is, we can come up with a forecast for the Bay Area. And we've done that, and it's on the chart here, it's in your booklet. And what we've determined, when I say we, the USGS and assortment of scientists around the Bay Area, about 100 people, came together in this study, and we determined that the likelihood of a future damaging earthquake in the Bay Area was about 62%, or basically about twice as likely as not to happen over the next 30 years. Now, this is a forecast just like if I were to say there's a 75% chance of rain in the next 24 hours. I hope you'd carry an umbrella or take some precautions. Same sort of thing. We're giving you the likelihood and a given period of time. We chose 30 years for a couple of reasons. That's the average home mortgage, so it should be a time period you're making decisions on. But also, it's a reasonable portion of an earthquake cycle. If we tried to give you a 1-year probability, the number would be so low you wouldn't pay attention. Just like if they tried to give you the 12-second forecast for the weather, you probably wouldn't pay a lot of attention to it. So that's our forecast. We can't say which of the faults. I think many of us most fear the Hayward Fault in the East Bay because, as I mentioned, we know that it's been very regular in terms of going off, and it's near the end of its cycle. But that said, the earthquake could occur anytime, could occur on any of the faults in the Bay Area or may even surprise us and occur in a fault we haven't identified yet. I think one of the final points I'd like to leave you with is the fact that this earthquake is going to occur without any warning. The 1906 earthquake, there of course had been earthquakes occurring for 70 years, but no one noted anything unusual in the days, weeks, and months leading up to that earthquake. It literally occurred without any warning. So I think it's really incumbent on all of us to be personally prepared, to insist that our communities are prepared, to worry about our schools, our places of work, because we all learned one thing from Katrina: we can't count on the federal government to do that for you. So I think I'll end there, and Mark and I will be glad to take any questions. Thank you. Sure.
Don't you think this couple is a barrel of laughs? All right, questions. We have quite a bit of time for questions. Let's start right here in the front row.
Okay, the question was regarding the timing and the rate of occurrence of earthquakes in the 19th century. We have, let me just say what we know historically about earthquakes in the Bay Area. We have a very convenient beginning for the historic record in the Bay Area, and I hope most of you are aware of this. This is 1776, and that was the founding of Mission Dolores in San Francisco, the first mission to be founded in the Bay Area. Over the next 20 years, the missions in the South Bay were founded, and then in the early 1800s, those in the North Bay. The significance of this is that the Padres were very good record keepers, particularly with regard to damage from earthquakes, because they could get money from the Vatican to repair the missions. So we have good records. And then, of course, by the 1850s, after the gold rush, there were many newspapers in the region. So we have a good record. So your question about earthquakes, at the very beginning of the mission records, there's no mention of earthquakes, even though in Southern California they'd experienced earthquakes. It seemed to be a very quiet period. And then starting in about 1832, we started having earthquakes in the San Francisco Bay Area that caused damage. In fact, in 1838, there was a magnitude 7 earthquake right here on the San Andreas Fault on the peninsula. And yet just 70 years later, we had the 1906 earthquake. So what we know is there was a 70-year period leading up to 1906 in which there was lots of earthquakes. In fact, there were 18 magnitude 6 or greater. So on average, over 70 years, that's every 4 years. Then we had the 1906 earthquake, a few large aftershocks, and then a really long, quiet period. We really didn't have an earthquake of magnitude 6 in the Bay Area until about 1970. So we had a 65-year quiet period, and this is a phenomenon that I refer to as a stress shadow, and we think that's the result of the earthquake on the San Andreas Fault relieving the strain on all the parallel faults. Now, plate tectonics has continued and has reloaded the faults, and the fact that we're starting to get earthquakes now makes us feel we're coming out of the stress shadow. And then you ask the question of what happened prior to that time. Well, we don't have very good records, but the fact that we don't see any earthquakes in the early part of the mission records makes us feel it was fairly quiet. And what we've learned from our paleoseismology, where we've actually dug these trenches across the faults, is that the period just before the Padres came, they had very good timing, was a very active period seismically. Every fault in the San Francisco Bay Area, all these faults you see here, had a major earthquake. We don't know the timing of those real well. It could have been 20 awful years or it could have been 80 awful years, but there were lots of earthquakes. That seemed to sort of shut the region down, make it quiet, and then there was a period of time, 60, 80, 100 years, when earthquakes began again, and then it took 70 years to have a 1906 event and shut it down. So it has been cyclical. Oh, the question was, what have Mark and I have done to prepare? Our Prius is parked right over there, and in the car, both our cars, we have a backpack. I have running shoes, a sweatshirt, a pair of jeans, food, water, a first aid kit, a space blanket, because I spend about half of my time away from home. So I think the car is one good place to have a preparedness kit. We have supplies at home. The camping material doesn't need to be stored away in closets. Put it in a place that you can get at it easily, and that can be some emergency supplies. So we have supplies at home, we have supplies in our car, and I hope we're ready. That's from my aunt. Whether or not global warming has anything to do with earthquakes. And I'll make a comment, and I'll let Mark comment on this too, if he'd like. If you'd asked me that maybe a couple of years ago, I probably said, no, what are you talking about? But in fact, not on a weekly, monthly basis does it have an impact on earthquakes. But what we do know now from a lot of different lines of evidence is that very small changes in the stress acting on the Earth's crust can trigger earthquakes. And these changes can be as small as filling a dam. Whenever we have pond dams around the world, earthquakes start occurring, and that's related to the weight of water being added to the Earth's crust. And what we're actually seeing is that some of the mass changes associated with glaciers melting or potentially ice sheets breaking off may in fact be triggering earthquakes or may cause an increase in earthquakes in the future.
The question is whether there's a correlation between water levels, water table fluctuations, and seismic activity. We do know that it's possible to trigger earthquakes by changing fluid pressure at depth. And that's because when you raise the pressure, say you're injecting water into an oil field and there are faults present, the pressure of the water tends to push the fault apart and makes it easier to slide. So there have been literally hundreds of examples in which water is injected to help push the oil out and winds up triggering small earthquakes. It's been seen in many other environments, as Mary Lou pointed out. Sometimes when dams are impounded after many years, the water pressure increases at depth. Earthquakes are occurring in areas where they're not expected. So we do know there's a physical link, and we understand why it happens, and some of the cases in which it happens are very clear-cut. There have been arguments that there are seasonal effects associated with the frequency with which earthquakes occur in different regions. And I think there are some signals there. They're weak signals, and I don't think it's anything that has a large, say, global correlation with large and damaging earthquakes, but there's certainly a correlation between water fluctuation changes and earthquake occurrence in some parts of the world.
Would you two like to say a word about the relationships, if any, between volcanic activity and earthquakes?
There are many earthquakes in volcanic areas, and there are linkages between perturbations in some places and responses in others. And now we know, for example, that some earthquakes, for example, the big earthquake that occurred in Alaska on the Denali Fault a number of years ago actually changed the rate at which earthquakes were occurring 1,000 miles away in Long Valley Caldera in Yellowstone. So very small perturbations of the natural state in volcanic areas did in fact change the rate at which earthquakes are occurring. And the reason for that is those areas tend to be in sort of an incipient failure mode, and not much of a change is enough to change the rate at which earthquakes occur. Now, maybe you were fishing for something else, and Mary Lou knows what that is.
Also, you see in the press often a mention of things like harmonic tremors.
Right.
So you want to say a word about that?
Sure. Many scientists who are interested in prediction of volcanic eruptions have a lot more to go on than those of us who are interested in trying to predict earthquakes. And that's because before a volcano erupts, there has to be a period in which magma moves into the Earth's crust from much greater depth. As that magma moves in, the volcano tends to inflate. That inflation tends to trigger small earthquakes, and the movement of fluids at depth, either magma or water and steam that is heated by the magma, moves through the fractures and faults that are already there. When that starts to occur, a special kind of seismic signal is seen, harmonic tremor, which is sort of like a steady vibration of the Earth's crust. So as seismologists and volcanologists are studying a volcano that seems to be coming alive after a period of dormancy, the things they're looking at is A, the occurrence of small earthquakes, B, the inflation of the edifice, implying that there's magma moving in from great depth to relatively shallow depth, And 3, these volcanic tremors that are telling us that fluids are moving through the pre-existing fractures and faults. And when these events start to come together, that's what leads to predictions of eruptions. And there have been any number of very successful predictions. They don't get as much press as they deserve, but the great eruption Mount Pinatubo in the Philippines a number of years ago was successfully predicted, largely by a team from the USGS. Clark Air Force Base was abandoned and was later buried in ash. Thousands of lives were saved as a result of a very successful earthquake prediction, volcano prediction, Freudian slip, volcanic prediction that was made on the basis of those kinds of phenomena.
I think I'll just add too, there is mounting evidence that nearby earthquakes can help trigger eruptions. Sometimes it happens within hours, sometimes it might be a few days, so there may be fluids involved. There's also evidence from Iceland that eruptions can trigger earthquakes nearby. So there is this interplay between the same forces that are driving the earthquakes are also allowing the magma to be released. And interestingly, and to get back to the climate change question, there's an earthquake, here we go, a volcano, the Pavlov volcano in Alaska, which had been noted for a long time, always erupted in the autumn and winter. And a seismologist studying that volcano up there now has done a very careful correlation of the timing of the eruptions. And these always occur during the major winter storms, so very low pressure. And what happens during these storms is that sea level rises about 30 meters. And that additional load on the volcano seems to be enough to literally kind of squeeze magma out of it, as though you were squeezing a toothpaste out of a tube. And in fact, during these storms, you often have big waves coming in, piling up water, so it's even larger load. So we are seeing very subtle changes in forces acting on the Earth's crust that can either trigger an earthquake, trigger a volcano, or literally help a volcano erupt.
The question was whether there was, is there any hope of using unusual animal behavior to predict earthquakes? There have been many anecdotal accounts of people reporting that a pet or some domesticated animal had acted unusually prior to the occurrence of an earthquake. But there have been a number of attempts to try to document those unusual behaviors and to use them in a systematic way, and they've all proven not to be useful. It's obviously a hard thing to calibrate, it's hard data to collect, and it's hard to know what signals that the animals might be detecting that aren't detected by conventional geophysical instrumentation. So we don't think there's much there. It's not proven to be a productive line of research. I don't think you could rule it out, but if your dog behaves unusually, it's probably not due to a forthcoming earthquake. The question is, if you pump oil from the earth, does that change things? It does change things, and in fact, when you do remove oil, the material surrounding the oil reservoir does respond. The stresses change, and you can actually trigger earthquakes, small earthquakes near the oil field, in some cases by removing oil, just as you can by injecting water, as I was saying. It probably has not been responsible for any large and damaging earthquakes, with the local exception. For example, the Wilmington oil field in Long Beach is right there, Long Beach Harbor, and there was a tremendous amount of subsidence, over 30 feet as I recall, and many earthquakes that were, while they were relatively small in magnitude 2 to 3, they were occurring at very shallow depth. So they weren't going to trigger a big earthquake that would affect the LA basin, but they certainly had produced very strong shaking in the Long Beach area. So it certainly is something to be concerned about. Yeah, the question is whether there are any extraterrestrial effects on earthquakes. And this is an interesting question because there's a phenomenon known as earth tides. We're familiar with the tides of the ocean responding mostly to the gravitational attraction of the moon. Well, the Earth also has tides, and the Earth deforms as a result of the changing gravitational attraction of the moon and the other planets. Now, these are very predictable. We know what they are, and we can model them. Now, it is reasonable to expect that if an earthquake is about to occur, as the earth tides change the stresses, that might be a triggering event. And it is true that in these in volcanic areas, which are producing small earthquakes all the time, there is a correlation between the numbers of earthquakes and these tidal cycles. There's a 24-hour cycle, an 11-hour cycle, and then there's cycles over days and weeks. And we see this correlation there. Now, in the late 1970s, I believe, a book was published called The Jupiter Effect. And it pointed out that there are certain times when the planets align, and Jupiter being a very large planet has a very big effect. That alignment causes an unusually strong earth tide. And that would be a time in which one would expect earthquakes to be triggered. Well, nothing happened. And we can go back through time and we can document the times at which this Jupiter effect had acted in the past, and it does not correlate with the times at which big earthquakes occur. So again, it's a modulating factor, mostly seen where there are many small earthquakes, but not diagnostic for the time of occurrence of really big ones, which are, of course, the ones we're most worried about. It's a good question.
Back to this.
Go ahead.
Let me just say one thing quickly, because she's too modest to say this. Out of her PhD study area, she took a piece of a fault and donated it to the School of Earth Sciences. It's posted on the 3rd floor, hanging on the wall in the Mitchell building. Come by and see it sometime.
The question was, what does a fault look like? And Steve related the fact that I carried a big chunk of rock up from a fault down because it had neat striations on it that showed how the blocks moved. So a fault is like a crack in the ground, but the difference between a fault and just a fracture is a fracture might just open, but a fault has to have some slip, some horizontal or some vertical motion across it. And the faults that we're talking about here extend down more than 10 miles into the Earth's crust. When they get into the lower crust, the rocks there are really more flowing, so we may not have a distinct fault plane. But in general, when we're talking about a fault, it is a fracture running through the upper part of the Earth's crust, and it's defined by having motion on it. Now, what does it look like? You know where Portola Valley is? You know where the Gould School is? Okay, well, you're looking at the fault all the time. It doesn't look like much of anything, does it? It's a flat valley. And it's a bit of a challenge for geologists sometimes to find faults, but we will look for things like changes in vegetation across them. Sometimes there's 2 different rock units superimposed, and it'll be a groundwater barrier, so there may be very different vegetation. We look for things like streams coming down that hit a fault that maybe are offset. So the stream comes down, all of a sudden it makes a right angle bend, and then it starts going down slope again. So there's a lot of ways to recognize a fault, but fundamentally it's a fracture upon which 2 rock surfaces have slid past one another. There's a very rigorous licensing review for the seismic safety of nuclear reactors. The question was about how do nuclear facilities plan for earthquakes, and do they? And in fact, as I was saying, they have a very rigorous review. It usually involves getting together a lot of experts trying to decide what is actually called the MCE, the maximum credible earthquake, would be for a site, and then predict how strong the ground motions might be and design for those ground motions. So I think we've done a pretty good job on that. I think the human problems at nuclear sites are far larger than the seismic ones. No, the question is that an international standard? In developed countries it is. I couldn't say for sure in many places in the Soviet Union where they were building reactors fairly quickly. The question was about the pattern of damage, and you can go to a dense residential area and you'll see maybe one house hardly damaged, maybe a chimney down, and in some cases you can look at 2 apartment buildings. One's totally collapsed and the other's left standing. So your question was whether or not this is related to the actual wave phenomena. Probably, because at that point a lot of waves are coming in, different frequencies superimposed. There probably is less of effect of variations in the wave amplitudes, but more related to slightly different soil types. One soil may be covering a buried channel, something like that. But most likely this is due to variations in construction style. And we see this all over the world, that we have great building codes, but a lot of corners are cut in building. And one thing I do want to say, I talked about a lot of doom and gloom. This typical California ranch-style home is one of the most earthquake-resistant structures around. A 1 or 2 story home, wood frame, that's got a lot of flexibility. It's going to give, provided it's not an older home that's not bolted down to its foundation. If you've got an older home, make sure it's attached to the foundation. But in general, those of us that live in single-family homes here in the Bay Area throughout California, it's highly unlikely that we're going to be really injured by our homes. Wouldn't that be great? The question was whether or not the 1906 earthquake and its relieving stress on parallel faults might have reset the Hayward Fault, its clock back to zero. I would say that's probably wishful thinking. It might have delayed the clock by 10, 15, 20 years. It's hard to be quantitative about that. It certainly did delay lots of activity. But remember, this average repeat time of 150 years for earthquakes on the Hayward Fault I gave you spans nearly 2,000 years. So there have been lots of other earthquakes. So on average, maybe it's the other earthquakes causing the variability in the system.
The question is about these creeping faults and earthquakes. Now, creep just means that the fault is moving continuously and slowly without generating seismic waves. And as I alluded to earlier, this has now been observed to occur in these episodes at very great depth in several parts of the world. And in fact, as we look in more places, we'll undoubtedly see it happening more often. So if a fault is locked near the surface and is creeping at depth, that's putting stress into the lock section and could bring the fault to the point of failure. Now, one of my colleagues in the geophysics department, Professor Paul Siegel, has been studying a phenomenon that's similar to this in Hawaii. And off the southeast coast of the Big Island, there is a seismic slip on a relatively flat fault. It can be thought of as like a giant landslide. And as that fault slips, it changes the stress in the surrounding crust and produces many small earthquakes. So it's not exactly analogous to this process of what's happening deep below the San Andreas Fault in Cascadia in the Pacific Northwest, in Japan, Central America, northern New Zealand, and elsewhere. But it's a very enticing kind of phenomenon because we know how now to make the observations to document it, and and as we study it in more places and over more time, we'll have a much better understanding of what it all means with respect to the long-term earthquake cycle. So it's a really exciting new area of research. No. Do we have earthquake insurance? It's high premiums and poor coverage. It's a personal decision. You want to say anything more about the policy? We agree on not having earthquake insurance.
No, I actually almost have scared myself into getting it in the last year. I get asked this question a lot, and I will say I'm a government employee, so I can't make any personal endorsements or recommendations. So I'm just giving you my personal opinion. I think a lot of us say what Mark just said. Well, poor coverage, 15% deductible. My home's worth $2 million. Not my personal home, but your home's not worth $2 million. Your lot is worth $2 million. If you want to rebuild your home after an earthquake, then what's the typical cost per square foot here? It's pretty high, higher than anywhere else in the state, probably higher than anywhere else in the country. After an earthquake, that cost is going to be double. Contractors will have more work than they can possibly do. They're going to be charging premiums. So if you have any questions about your home, if a lot of your personal assets are tied up in your home, pay a structural engineer a few $100s to come out and tell you how much damage is likely to occur to your home. And then you can weigh the cost of the premium versus what you would get back. I think it's really important for people to remember, and I think a lot of New Orleans residents were rudely awakened to find this out. If your home's unlivable after an earthquake, your mortgage is still due. That's still your home. So you're going to be paying temporary living expenses somewhere else, and you're going to continue to pay the mortgage on the home. Nothing changes about that, unless you want to walk away from the home and give the lot to the bank. So I've become less cavalier about the answer to that question. I think it's a personal decision, and people that have nearly all their assets tied up in their home, it may well be a very good investment. A question was about cell phone technology and how likely that is to be operable after a major earthquake. I was part of a City of Berkeley planning exercise. It was actually pretty impressive. 150 city employees and university employees came for a morning of discussion about earthquake hazards. And we had a fire chief from San Diego at the meeting, part of the International Association of Firefighters, and he had been designated to go down to New Orleans and help out. And what he described there was pretty chilling. Now, of course, that was a hurricane, there were strong winds, but strong shaking would have similar effects. The power lines were knocked down, the phone lines were knocked down, so landlines went immediately. Cell phone towers were knocked down, or cell phone towers didn't have power, they didn't operate. So effectively, cell phones did not operate. And the most chilling thing that he told us is that all the emergency responders had satellite phones, but lo and behold, so did all the press. And all the press were down there keeping their satellite lines open continuously, so if something happened, they could do a live feed. So the firefighters, and this fire chief described going around, he wasn't helping in New Orleans proper, but trying to help in the surrounding area. And he actually said they came to one fire station that was stranded. The guy was trying to communicate. They had no phones to communicate with. He literally dropped a message down in a bottle to the fire chief. The fire chief scribbled what they needed, and then they hoisted the bottle back up to the helicopter. So that was the sophistication of communication after Katrina. And I don't see any reason why we will expect it to be any more sophisticated here. As far as I know, there have been no special measures to harden the cell phone towers in this area.
The question is whether there's a part of the world that does not have earthquakes. And there are many parts of the world that have very infrequent earthquakes. They're cold, often. No, seriously, you know, there are many regions which are actually constructed out of parts of the Earth that are billions of years old and extremely stable and produce relatively small earthquakes. And that's one of the useful things you can see on such maps. So perhaps when the session is done, pick your favorite place. It's the potential for earthquake prediction based on electromagnetic waves, and what was the other part? And thermal anomalies. There are such reports, and in fact, a scientist in the electrical engineering department here, Tony Fraser-Smith, documented a very interesting change in the low-frequency magnetic field with an instrument that was located in the Santa Cruz Mountains, essentially directly above the nucleation point of the Loma Prieta earthquake. And by doing some geophysical modeling, he could actually come up with a plausible scenario about what was happening in the Earth at depth that produced this signal that was observed. On closer scrutiny and trying to extend that work to other places, it's not proven to be particularly robust. For example, large aftershock, you know, they take the instruments down after an earthquake occurs, try to measure what happens after a when large aftershocks are occurring, and no signal has been seen, and no signal of its type has been seen associated with any other earthquakes in the 17 years since Loma Prieta. So it's certainly possible, but again, it's one of these isolated observations which may or may not, you know, be tied intimately to the occurrence of the earthquake, but has not proven to be a basis upon which short-term earthquake prediction becomes, you know, implementable and foreseeable.
I'll just add to that. One of the real problems we have is there's a lot of natural variability in the Earth, and a lot of times someone will see some sort of intriguing correlation and they'll say, let's go look before another earthquake. And they say, looks like there was a thermal anomaly there too. The problem is that, and these happen to have been noticed in the Mojave Desert, is that no one did sort of a background study of the whole Mojave Desert to say, do we see these signals maybe once a month just anywhere naturally? So the problem is that there's been somewhat a selective study of this. They only look in places where they think there might be a correlation rather than doing the general study first.
The question is whether small earthquakes are beneficial with respect to the ultimate occurrence of a large earthquake. It is true that when a small earthquake occurs, it releases a small amount of the energy that was stored up. And so in an absolute sense, you could say that many small earthquakes result in there being less energy to be released in a very large earthquake. But when you actually kind of do it more quantitatively, what you see is that the cumulative effect of all the small earthquakes is extremely small with respect to the energy that is eventually going to be released in the big earthquake. So yes, it's real, but it's of such a small cumulative magnitude that it doesn't ultimately affect the earthquake cycle. But of course, it's the regional occurrence of small earthquakes, or moderate earthquakes, the kind Mary Lou was talking about preceding 1906 in the 19th century, that's telling you that there's a lot of energy built up in the crust. And while each one is relieving a little bit, ultimately it took the 1906 to relieve all the energy and actually reduce the energy level down and to cause this stress shadow that she was talking about.
Really, the heart of this gets back to this factor of 30 I was talking about for every step in magnitude. So to go from the 1906 earthquake to Loma Prieta, that's a factor of 30. If we went down to a magnitude 5.9, it's 30 times 30 is 900. So you need to have a whole lot of tiny earthquakes to sum up to one big earthquake.
The question is, how are the GPS instruments installed and how do they operate? The GPS instruments work by, of course, observing signals coming from a constellation of satellites. So they have to be, the antenna has to be at the surface. The way the instruments are actually attached to the Earth requires them to be anchored some tens of meters just so they're not moving around with the soil. But they're basically measuring the deformation of the Earth's surface and relative deformation of 2 points with respect to each other. Oh, there's a tremendous technology called INSAR, Interferometric Satellite Synthetic Aperture Radar, which can actually show you how the entire Earth's surface is deforming. And this is a fantastic technology which, when used with GPS, gives geophysicists a remarkable view of deformation. Volcanoes have been seen to kind of breathe, inflate and deflate without eruptions. Deformation associated with the earthquake cycle has been observed. Even changes in the Earth's surface associated with seasonal changes in the water table have been observed. Unfortunately, INSAR is not yet being implemented broadly enough to be of adequate use. But that's a technology we know is there, we know is available, and we know can contribute very substantially to research in all of these fields.
Last question this side. Yes, right there. Yes, you.
That would only happen when the question was whether or not seismic activity could reach equilibrium and stop, basically, right? That would require plate tectonics to reach equilibrium. Plate tectonics is driven by the internal heat of the Earth, which is driven by radioactive decay of elements in the Earth's core. So it certainly won't happen in our lifetime because this has been going on for several billion years.
I'd like to thank Mark and Mary Lou for their insights today. And thank you all for coming.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.